Hello everyone. In this video I would like to finish the information from section 13.1, other mathematical systems and groups. Okay, so here we have another example, right? And this is a mathematical system composed of the set x, y, z. And then we have this little operator, a circle, and we can just read that as a circle. So we don't really know what this is doing, but it's just a way of combining elements in the set. Okay, so we could talk about x circle z, and then that would just equal whatever answer we get when we combine those two things. Alright, so we talked before about properties that a mathematical system can have. So take a minute, review if you need to, if you want to pause the video and recall what those are before we move on. Alright, so the 5 properties we are checking would be closure, commutative, identity, inverse, and associative. Okay, so closure first of all. And if you remember how to do this, just pause, see if you can do this on your own, then check your answers. Okay, closure property, see if all of the answers that you get in the inside of the table are elements from this original set that makes up the system. And yes, they are. So this is a closed system. Okay, commutative. Find the diagonal, and then look at things on either side and see if they match. And they do. Oh, just kidding. No, they don't. Okay, some of them do. X. All right, these are both x's. So y plus, or not plus, y circle x is the same as x circle y. Okay, and z circle y is the same as y circle z. But here we have two that are different. Okay, so z circle x is y, but x circle z is z. Okay, so two different answers, so this is not a commutative system. Identity. Okay, so look for a row or column that matches x, y, z. And okay, we've got one here, so perhaps y is the identity. So let's check the row for y as well, and I see x, y, z, which matches the original element order at the top. Okay, so that works. So that tells us that yes, the identity property does hold, and that y is the identity. Okay. All right, inverse property. Do we always have some way to get back to y? Is there always something that I can add to another element to get y? Okay, so let me find the y's that are answers. And this looks good for z. Z circle x is y. All right, and for y, y circle y is y. All right, but now for x, if you look across your row, here are all the answers you can get when you combine with x, and it doesn't work. All right, x circle what is the identity y? Nothing. Nothing. Right? Now if I go the other way, I do have something that I can circle with x to get y. Okay, if you're looking at this one down here, z circle x is y. That is true, but I don't have anything that I can fill in this direction. And that's the problem is, that this is not a commutative system. All right, so because it's not commutative, it actually ended up affecting the inverses, and we actually don't have an inverse for x. Inverses have to go both ways. Like for example, if you had 5 plus negative 5 is 0, those are inverses, but we need to make sure that it also works the other direction as well. And it doesn't, okay, in this case. So we say x does not have an inverse, and so the inverse property does not hold. Okay? No inverse, not commutative. Associative. All right. Now, it could still be associative even if it's not commutative because we're switching the order or the grouping, so the order in which the operation is done, but we're not switching the elements themselves. All right, so try it out. Let's do x circle y circle z, and then we'll try x circle y first, and then circle that with z. All right, so first y circle z, okay, y circle z is z, and x circle z is z. Okay, and we'll try the next one. X circle y is x, and x circle z, look, this one matches. We already figured that one out. We know that that's z. Okay, so those match, and that might make you suspect that this is an associative system. Okay, so you could try a couple other examples, convince yourself one way or the other. Okay, so you're just making a conjecture at this point. All right, so that concludes that example. And groups, this is the second part of the section. All right, what is a group? Well, a mathematical system that has some of these certain properties is said to be a group. So not all of them are. For example, the one we just looked at, this is not a group. It doesn't have the inverse property. Okay, but a math system is a group if it has closure, associative, identity, and inverse properties. Okay? Now on top of that, if it's also a commutative group, then we call that an abelian group. Okay, and this is named after someone, so that's why it's capitalized. Right? Abelian group has all of those other properties, closure, associative, identity, inverse, but then you're also adding on the commutative property. Right? Real numbers, we know that they have all of these properties. So real numbers, we would say, those are an abelian group. Okay. Now we do need an operation, so we have to specify real numbers and addition is an abelian group, and real numbers and multiplication is also an abelian group. Okay, let's try out a couple other examples. The natural numbers. There's your symbol. Do the natural numbers under the operation of addition form a group? And then an abelian group. Okay, so you're really just checking the same properties that you have been already, but we're just giving it a special name if it happens to have all of those properties. Okay, so closure. When you, under the operation of addition, so if you add a natural number, we'll just call it n, plus another natural number m, do you always get another natural number? All right, well, if you think about the natural numbers, those are your counting ones, 1, 2, 3, 4, 5, etc. Right. And if you add natural numbers, it's kind of just like counting up, so you're always going to get something that's higher. The sum is always going to be greater, so it's going to be another natural number. So yes, this property does hold. Okay, commutative. All right, if you add two natural numbers together and then you switch the order, is the sum still the same? 1 plus 4 equals 4 plus 1. Yes, that's true also. Okay, the commutative property. How about identity? Okay, natural number plus something else, another natural number that equals that natural number. Okay, so 5 plus what equals 5? Well, we know the answer is 0, right? But what do you think? Can that be the identity for this system? Well, we said that an identity has to be something in that set, and 0 is not in the set of natural numbers. So it's almost like it doesn't even exist for this problem. So there is no natural number that we can put here that would make this equation true. So there actually is no identity for the natural numbers. All right. And right there we can stop, right? Save yourself a little bit of work. You're just asked if this is a group, and if it doesn't even have the identity property, then it's not a group. We don't even need to check associative or inverse. All right. And if it's not a group, then it's not an abelian group, because an abelian group has to have all of those group properties as well as being commutative. Okay, so it doesn't have an identity, so it's not a group. Okay, so the answer would be no. All right, how about this set? A very small set. All right, this one is a finite set, -1, 1. Does this form a group under the operation of multiplication? Okay, and we're just thinking of normal multiplication here. All right, so let's check closure. And let's make a little table here. All right, sometimes an operation table is a good way to quickly see which of these properties hold. Okay, so here's multiplication. List your elements at the top and down the side. And then fill this in. Okay, so 1 times 1, or we'll start here. -1 times -1 is 1. -1 times 1. 1 times -1, and 1 times 1. Okay, so what do you think about closure? Okay, yep. Okay, all of the answers are things that were in the set to begin with. So this is a closed system. Commutative. This one's really easy to check. Okay, two of our sums here, you're just adding the same number so that, it doesn't look any different when you switch those. But we really just want to know, is -1 times 1 the same as 1 times -1? And yes, it is. Okay, matches across the diagonal. So this is a commutative system. Okay. Identity. All right. We only have 2 elements to check here. Is there something -1 times something that still equals -1? Well, yes, there is. A 1. Okay. Now, if that's the identity, then it should also work for 1. 1 times what equals itself? And it does. Right? And we already know this is commutative, so we don't need to reverse the order and check that way. Right? So, yes, this does have an identity property, and the identity is the number 1. And inverses. Okay, do we have a way to get back to the identity? So -1 times what equals 1, the identity. And then 1 times what equals 1, the identity. All right, well, -1 times -1 is 1. And 1 times 1 is 1. Right? And now this one doesn't have to match. Numbers can have different inverses, just like 5 and 4 would have different inverses for addition, different things that add up to equal 0 with that number. Right? But the important thing is just that an inverse exists and that it's something from this set. Okay? And the inverses are -1 and 1, and that works. Okay, so this does have the inverse property, and then each number has its own inverse. So the inverse of -1 is itself, and the inverse of 1 is also itself. And then finally, associative. Okay, so let's try it out. -1 times 1 times, we'll pick 1, doesn't really matter. Is that the same as -1 times 1? And that product times 1. Okay, well, the first one, 1 times 1 is 1. -1 times 1 is -1. And the second one, -1 times 1 is -1 times 1 is -1. Right, those match. So at least in this example, we'll make the conjecture that this is an associative system. Okay. Okay, so we've checked all of these properties, and because the system has the closure, identity, inverse, and associative properties, that makes it a group, yes. Okay, it is a group. Then to be abelian, we have to check, does it also have the commutative property? And we already checked that one. Yes, it does. So yes, this is an abelian group. So this is an example of a system that is both things, a group and an abelian group. Right, our previous example was neither. Now, it could just be one, it could be a group, but not abelian, as long as it's not commutative. All right, and that concludes section 13.1. Thank you for watching. I'll see you in the next video.